What I'm going to do is I'm going to be talking about something that's not in the program. This was the blessing of the conference organizers. So I decided to kind of change the topic of my talk. And I'm going to be talking about something that meshes really well with what we've been hearing out in the other two talks this morning, and that's molecular gas. Specifically, I'm going to be moving away from LOSI. I'm going to be talking about molecular gas measurements of high redshift galaxies, kind of using the deepest CO1 to 0 maps that exist for galaxies outside the local universe that we've been doing with the VLA. And we're going to be using these molecular gas observations coupled with some other blind observations in HDF North done by people here at MPIA like Fabian Walter and Roberto De Carli to try and understand whether or not we really have an idea of how star formation is fueled in high-Z galaxies. I'm going to be looking at a distant cluster of galaxies that we've been studying for a while now at Z 1.6. And despite this whole meeting being very explicitly about centrals, because these deep observations are at the location of a cluster, it's going to be unavoidable to talk about kind of the supply side of the decline of star formation in galaxies. So it's kind of the road to quiescence, I should say. And so this is University of Kansas, by the way. It's where I spend most of my time when I don't get to spend my summers in Heidelberg. And if you're ever flying over the United States and have a parachute, I really encourage you to come and visit. It's actually not flat like people think of Kansas. There's not tornadoes. It's hilly. It's wooded. It's beautiful. Please come and visit.
Hilly is a relative term.
It's not as hilly as here, but it's not as flat as western Kansas. I'll put things in perspective. Okay, so we've heard a lot this morning and in recent years about molecular gas being very important for understanding the processes that regulate star formation. And this has been driven by a revolution in the capabilities of millimeter wave interferometers that have allowed us at LOSI to get extremely high resolution maps of nearby galaxies and understand the spatially resolved links between star formation and gas supply, like we heard this morning. But it's also given us the sensitivity to explore molecular gas contents in kind of what you might call first starbursting galaxies, things significantly above the main sequence of star formation, and also totally run-of-the-mill star formation galaxies, which we now know at high Z are things that we would here call ULIRGs, but are actually forming on this main sequence of star formation. And so this plot shows a summary from Carrilli and Walter, and some of the bottom stuff is cut off, but this is from a review by Carrilli and Walter, where it shows the infrared luminosity on this axis versus the CO line luminosity. And the infrared luminosity is kind of a proxy for the obscured star formation. The CO line luminosity is a proxy for the molecular gas modulo the conversion, the alpha conversion. And so you see that, as we've seen before, low-Z galaxies and high-Z galaxies all lie on this relation. You can express this in total quantities like this. You can also express this in surface densities, as I'll do later, much more similar to the traditional Kennicutt-Schmidt law. And what you see is that the star formation tends to be very well correlated with the molecular gas. Now, if you converted these star formation rates and molecular gas masses into a gas consumption timescale, you would find that for your average galaxy on the main sequence, right around here, you would get that things have gas consumption timescales of around 0.7 gig-years. This is stuff from recent work, especially this was shown in Tacconi 2013 from the FIB sample, a big sample of galaxies at Z of 1 to 2.5 with lots of plateau de Broglie interferometer observations. So the thing is, many of the galaxies that were studied up to this point were kind of these extreme galaxies, things above the main sequence. We're just now being able to start massing large samples of galaxies at what you might consider normal star formation rates. And it's these I'm going to talk about today. Another interesting thing is that if you actually look at the molecular gas fractions in galaxies over cosmic time, and this is again by this review from Carrilli and Walter, you find that the molecular gas fractions are dropping very rapidly down to Z of 0, and that this kind of mirrors the decline in the global star formation rate. So while some of the total decline in the global star formation rate density must come from quenching, we know this has to happen, it also comes from simply the reduction of star formation rates in star-forming galaxies. And we think, given what we saw in the last plot, that this is potentially driven by supply-side economics. It's the cutoff of the gas supply.
And selection effects.
What?
And selection effects, maybe?
And selection effects, maybe. That's actually part of my talk. Thank you for the foreshadowing. So, that's okay. So In addition, so given this, what we really want to know is what kind of governs star formation at high redshift. You know, we've got these really nice early looks at the gas contents of high redshift galaxies. We'd like to know, if you study the population in kind of an objective, as low bias as possible, what governs star formation. And again, despite the focus of this conference on central galaxies, I also think it's important to understand, you know, how massive galaxies and high Z dense environments evolve. Because if you look at massive central galaxies today, their stellar mass may have been in galaxies that were satellite galaxies at this point, right? So if you want to understand the total star formation history of central galaxies, you have to understand things in all environments at high redshift. And there's obstacles to this. There are a few really robust gas measurements that should be CO 1 to 0, not just 1 to nothing. And that, as I'll show in a minute, lets us get robust measurements of the gas at high redshift. There are very few, now I think 2 basically, deep blind CO studies at high redshift that don't select things that are kind of forming stars extremely or selecting things explicitly known to be able to get detections, but really just pointing to the section of the sky and trying to do as close as possible to a molecular gas mass selection. And finally, there's no tests really of molecular gas abundances in dense environments at high Z. So I want to ask, are we missing galaxies with interesting properties that can tell us about what regulates star formation, and how does supply-side regulation of star formation work in urban environments at high redshift? So to do this well, because the effects may be subtle, you want to get robust measurements of the gas mass. We want to get molecular masses to study the baryon budgets, the mass fractions. We'd like to understand the gas consumption timescales, and eventually the physical conditions of the gas. We use CO as a tracer of molecular hydrogen because it's the easiest thing to do, and because it tends to be a pretty good tracer, modulo this conversion factor alpha, which I'll talk about. But there's also, you know, because of purely technical reasons, people have been really focusing on higher level CO transitions. So this is a plot that shows the flux of higher transition CO lines compared to lower transition CO lines as a function of the transition, the upper level transition, for everything with a CO 1 to 0 measurement normalized to CO 1 to 0. So it's completely artificial that all the CO 1 to 0 points overlap, but the point is there's a very large range in the excitation by a factor of 3 going from your CO 3 to 2 line down to your CO 1 to 0 line. So if you want to get a robust gas mass, it really helps to do the hard work and go to this intrinsically fainter CO 1 to 0 line to at least assess if there's any biases in the existing samples. The JVLA is uniquely capable here because by having a higher frequency capability with the upgrade, we can now access CO 1 to 0 at high redshift, and by having its updated correlators, we have a larger bandwidth that lets us look at galaxies without knowing their exact precise redshifts. I'm going to talk now about our very deep CO observations of a Z of 1.62 cluster. Just a little background on the system. It was selected as an overdensity of IRAC red sources. So these are not red sequence galaxies. These selects galaxies independent of their spectral energy distributions. And if you just plot the surface density of the galaxies in this cluster right there, it's the biggest overdensity of the UDS. We followed it up with lots of ground-based spectroscopy and with wide field camera 3 Grism spectroscopy, both from 3D-HST and from our own program. And we have over 30 spectroscopically confirmed members in this cluster. I call it a cluster and not an overdensity only because it actually has a diffuse X-ray detection. And the stellar mass, the dynamical mass is something like 10 to the 14 solar masses. This will probably turn into something like Virgo. It won't turn into something like Coma. What's interesting is that in this cluster, and we find this in more and more clusters at high Z, there are many star-forming galaxies in the core of this cluster. This makes sense because at some point, the dominant early-type galaxies, or passive galaxies in clusters today, have to have formed their stars. We're seeing the epoch where their star formation was turning off at these high redshifts. So what we did was, we took a single VLA pointing at this cluster. So this surface density map is all the galaxies that went into finding the overdensity. All these yellow diamonds are spectroscopically confirmed members of the cluster. The green ones are CO detections I'll talk about in a minute, and these are non-members that we could have observed CO in, given their redshifts. So we've taken the deepest ever CO 1 to 0 map with the VLA, in fact I think with any telescope at high redshift, on this cluster. And so it's really kind of a deep blind survey to try and detect the gas. We have about 45 hours on source already, and we're getting another 60 hours this summer. But already we're the deepest survey that exists on this. So these are our 2 detections. These are both candles images here. This is the CO detection. The formal signal noise is around 5, but in terms of kind of the likelihood of these being spurious detections, it's reduced even more because we have spectroscopic information. This source right here has a spectroscopic redshift that coincides exactly with the CO redshift. And here, this is consistent both with the cluster redshift and with the GRISM redshift from 3D HST. This is an X-ray AGN, but as I'll show in a second, the AGN does not have any dominant energetics in the infrared, or pretty much in any wavelength. And this looks like a I won't say rotate, it looks like a disk, right? Just from the morphology, it's elongated, right? We don't know the dynamics. We don't have spatially resolved maps of this yet. But if you interpret these full width half maxes as a sigma, these are around 280 kilometers a second. These are massive galaxies, and I'll show that. And right now, in context of their stellar mass and where they lie with respect to the global population, this is the main sequence of star formation.
Right.
What?
Which, do you know, can you tell that it's the circle blob rather than the blob?
Yes, I can. That's the beam size.
Okay.
The red is our beam, so these are not blended.
Got it.
And in fact, this is not the cluster redshift, even though it's close together.
Oh, that's amusing.
So this is, the evolution, the main sequence star formation from Woods et al. And if you put our sources on there, they're right there. So this source right there is kind of right at the tip of the main sequence. This ring here is significantly below in star formation at roughly the same mass. These are 10 to the 11 solar mass galaxies. These are massive galaxies in this cluster. And if you actually look at their SED fits, these are, as you'd expect from the fact that they have relatively high star formation rates. These are obscured. This is fit using MagFizz, a code from Elisabetta de Cunha, that self-consistently models the extinction of the starlight in the optical and how it's then re-emitted in the infrared. So it actually has been shown to do a good job at predicting the infrared flux given just an optical SED. For these two, we have Spitzer observations. For this one, we actually have Herschel observations. So the infrared luminosities are reasonably well constrained. So that's the background and the context. What do the gas properties of these galaxies look like? These are the gas masses of these galaxies compared to their stellar masses. These are massive galaxies with very high gas contents. The open circles here are from the FIBS sample. This is a big sample, a big survey being led out of MP. It's actually completed. They're now onto FIBS 2. It's being done with the Plateau de Boer interferometer. And so these are a bunch of galaxies selected, many of which are on the main sequence of star formation at Z of 1 to 2.5. Our galaxies are both at the high stellar mass end and at the high molecular gas fraction mass end of these things. Their gas fractions, depending how you phrase it, the baryonic gas fraction is around 60 to 70%, and there's more gas than stars in these galaxies. So now we can take these galaxies and we can plot them on this kind of pseudo-spatially integrated Schmidt plot, and they appear here. So these are these 2 points, same exact plot I showed before. These are our two galaxies. I've supplemented them with two other sets of points. The first are these right there, which are from a blind survey of the HDF North from de Carlio. So they literally detected lines in their data cube and then went back and found the galaxies. Ours is kind of blindish. We knew that there was star formation in the cluster. We pointed there, but we didn't target individual galaxies. So both of these are more of a CO line luminosity detection than something like an infrared luminosity detection. And we find that our galaxies really hug this outer envelope of the relation. This is a stacked spectrum. We have 60, as you'll from here, what's nice is you see that we have many spectroscopically confirmed galaxies in our one pointing. Right? Even though we only detect 2 at our depths, we can stack all the rest. You don't get as big of a signal noise gain as you'd like because you don't know exactly the redshifts for all these, so you have a big window when you're trying to assess the stack. But we can place at least constraints that at this point aren't yet interesting, but will get better with better redshifts and better depth. But you see that these things have low star formation rates with respect to their CO gas masses. This is also true if you plot it in terms of a more traditional Kennebec-Schmidt plot, and you plot the surface densities, where we've used the sizes from the candles 3D HST, from the candles imaging. These things really have very high molecular gas surface densities, and they're significantly low on their star formation rate density.
So what do they use for the alpha?
Yeah, I actually just now realized I didn't address this. So we used a Milky Way-like alpha CO, and we tested whether or not this was applicable. We have kind of sizes for these galaxies. We have velocity dispersion, so we assumed either circular motion or not, and tried to estimate the dynamical mass. And if you use a Euler-like alpha CO, so an alpha CO around 1, you actually underpredict the baryonic mass for one of these galaxies is a factor of 5 below the total mass, at kind of 5 sigma level. And so we don't expect these things to be that dark matter dominated. Whereas if you use a Milky Way-like alpha CO, or even something like an alpha CO 3, then you get something totally consistent where the baryons and the dynamical mass kind of agree. So we think using a higher alpha CO is appropriate for these sources. But if I change this by factor of 2, it doesn't really change the conclusions at all. So what's preventing the CO from forming stars?
Well, the nice thing is that at least in the observable plane of infrared luminosity,
Yes.
it's the CO that you're offset, right? So it's an
Yes.
unusual galaxy. How you interpret it is TBD.
Exactly. So but you can imagine strangely varying alpha COs across this. But you're right. Even in the observable plane, it's interesting. This may come out of the fact that we're doing a gas aligned luminosity selection. We're selecting this way as opposed to this way. We don't know yet, right? We only have 4 galaxies basically.
Oh, it's not that upset, right? So it's not on the distribution. So.
Yeah, it's not like these are way outside the distribution, but I'll show you in a second why they are, I think, even more interesting.
Greg, how do you get a CO science?
We don't. So there's been work using spatially resolved CO maps that have shown that the size measured in the optical is actually pretty well correlated with the CO size. Until we actually get, wider configuration, high resolution configuration, we won't know the CO size. We're trying to do that. We can't do it with VLA. You saw how long we exposed for these. We have to try and do it with HOMO. Can't even do it with PBI necessarily. Maybe with PBI, but it'll be hard. So why do these things have all this gas and not forming stars? Are the physical conditions of the gas different? To do this, we need to understand the excitation properties of the gas. Or is the gas somehow being stabilized? We heard these 2 really nice talks about different ways to stabilize gas against star formation. We have no idea if that's effect here, but we need to do high-resolution deep studies to understand this. We can rephrase this by also talking about what's the gas consumption timescale of these galaxies. And again, this bears back to how we compare these things detected in kind of blindish surveys to the stuff detected in these IR-selected surveys. So the field galaxies have gas consumption timescales of around 0.7 gigayears. So this is, in observed space, infrared luminosity over CO line luminosity versus infrared luminosity. You can kind of naively convert this to a gas consumption timescale by saying, okay, the phi r gives me the star formation rate, I assume a constant star formation rate, and I say how long will it take to use up my gas. Incredibly simplistic. If you do that, that's where you get this 0.7 gigayears from. Now, if you plot our galaxies and the ones from the HDF North on this plane right here, they have gas consumption timescales that range from about 1 to 4 gigayears. And I would claim that, especially for R2 galaxies, this is really kind of a lower limit. And the reason is because these things are in a massive cluster, right? Or at least they'll turn into a massive cluster by Z of 1. At Z of 1, clusters are dominated by quiescent galaxies. 80% or more of the galaxies at 10 to the 11 solar masses are quiescent in Z of 1 clusters. So while it could be that we were kind of unlucky, and these are the few galaxies that happen to not be quiescent at Z of 1, it's more likely that these galaxies have to have shut off most of their star formation by Z of 1. That implies their star formation rates will be declining, right? And so that's one possibility. But the odds of them increasing on the Z of 1, I personally wouldn't favor that, but we don't really know. The point is this assumes constant star formation, and it neglects gas recycling. So probably the gas consumption timescales are even longer than this. The problem is there's about 2 gigayears from Z of 1.5 to Z of 1. Right? And the gas consumption timescales border on that level. So these kind of lower consumption timescales for field galaxies were used extensively to argue for the need for lots of gas accretion onto galaxies. We can't possibly keep up these star formation rates if we don't keep funneling gas in. So it was really a nice supporting picture for these cold flows and stuff. These things actually don't require gas accretion. In fact, I would say they kind of argue against the need for any further gas accretion. And that may be easily understandable for our galaxies, these two, because they're in a massive halo. And so they may be cut off from their kind of gas umbilical cords. It's harder to understand for these galaxies here, but we also don't know their low Z descendants as well. Thanks. I'm almost done. So it really, for these galaxies, being in a cluster is actually nice because it allows us to do somewhat better job matching the evolutionary descendants. We can't do that with these small numbers of these galaxies here. We don't know number densities, right? So we can't actually do anything like a constant number density evolution. So is this a sign of some kind of environmental truncation of gas accretion? We don't know. So the only way to address this is by actually pushing these kind of very preliminary studies farther. Just to summarize, we have 2 CO1 to 0 detections in this cluster. We kind of couple that to these blind detections, which are actually the higher transition from the HDF North. But our detections alone increased by 50% all high redshift CO1 to 0 detections. This is hard work, but it's interesting to see how these kind of this slog gets us new information about the galaxy population. One of our observational conclusions is that these things have high stellar mass, high gas fractions, but low star formation efficiencies. And the question that's associated with that is what keeps the gas from forming stars. The second is that I think there's no additional accretion allowed given the star formation rates and the gas supplies. And so is that a sign of the truncation of accretion in these massive galaxies that we don't see when we look at kind of the average field population? I think this highlights the importance of blind CO surveys, which are hard sells to the TAC but are important. And I think we need to do dense high redshift environments, both because they're easy and because they're fun and interesting. Okay.
Questions?
So combined with Sharon's talk, how about the scenario as an alternative that this gas not forming stars precisely because it is streaming towards the center right now, talking about this galaxy. Then it will set up a nuclear starburst in an AGN phase, and then it will do some proper quenching, and it will have your redshift 1 post-starburst type galaxy. Everything's taking this.
So, I mean, yeah, that might work. I don't know. I mean, the only way I can even possibly address that, given the data we have in hand, is the fact that the kind of Z of 1, we think the AGN fraction, Paul Martini wrote a paper that said the AGN fraction is higher in clusters, but that's like kind of very circumstantial, right? I think to really understand this, we have to do spatially resolved studies of these galaxies to find out what their gas motions are like. So you look at the KMOS 3D stuff and the SIN stuff, studying the ionized gas. This stuff has been amazing in really trying to understand the gas properties. I think we have to do this now in CO in these galaxies. People are doing it, right? But we can't just do it in IR luminous, selected to be IR luminous galaxies. We have to do it in these kind of objects as well.
So to which extent can you, because the field galaxies in the Hubble Deep Field North are doing exactly the same thing, which
Yes.
makes me think it's probably a generic. My suspicion is this is what galaxies look like if they're not the very most luminous freaks. So I guess my question is, do you have insight into the structures of many of the other galaxies that are in the compilation of
Okay, so
Beryllium Altar, because that might give you some insight into, oh, you know what, these are some of the very few relatively non-crazy disks that are actually probed at high redshift.
Okay, so two things. First of all, the ones in the Fib sample, so these galaxies here are not extreme starbursts. These are on the main sequence. So as far as normal goes, they're normal in CO2. So some of these are. These red and orange and green dots are kind of extreme. These were selected kind of BMBX objects, more or less on the main sequence. I mean, that's at least, right? So if you plot them on the star formation stellar mass diagram, they look like they're on the main
Well,
sequence.
they're selected, let's be careful.
But they're selected to be IR luminous.
Right.
That's right. So that's right. So we don't know the difference. So it could be that these are unusual and that maybe they have the most settled or the most settled gas disks, right? We don't know. I mean, we don't have any 2D information on this at all. So I could speculate what might be causing this. One of, if you look at the HST images at least, this looks like a beautiful, I mean, just my eye said, oh, it's a disk, right? I don't know if it's a disk, but it looks like a disk.
It's elongated.
This is compact, and again, it has a high velocity dispersion, so it's the width of the CO line is just as broad as this one, right? So it's not presumably, if it's a face-on disk, it's an extremely odd one, right? Or it's not a disk at all. So I can't support that statement with these yet.
Okay.
And I don't know why the HDF North galaxies look the same as these. So, there's two aspects. One of these is what's keeping the CO from forming gas now. We can ask that for both sets of galaxies. The second question, which we can only ask for ours because we know the descendants a little better, is what happens to them in the next 2 gigayears.
Jay?
Yeah, so just along the same lines, there's basically only very, very few galaxies even now that have a width of over 600, right?
In the present day.
In the present day.
Right.
So you're high redshift, modest redshift. This is not a normal galaxy. No.
It's normal at high Z. So these kind of sigmas are not uncommon at Z of 2.
So you're claiming that the typical high Z galaxy is a very high mass galaxy?
No, your typical 10 to the 11th solar mass high Z galaxy is a high mass galaxy by definition.
The point is this cannot evolve into a spiral today unless it goes dead.
Yeah, of course.
Correct.
Well, these won't evolve into spirals because they're forming stars now at this is forming stars at 200 solar masses a year, and it's already 10 to the 11th solar masses. It will
I'm
not
not
be a
worried
spiral.
about the mass, I'm worried about the velocity.
No, there won't be a spiral today, right? Period.
It's an elliptical.
It's an elliptical.
Or it's-
These are going to be the cluster ellipticals
Right.
at Z of 1, period.
Second point, given that, how are you sure that you're actually measuring kinematic motions and not winds, molecular, high velocity molecular winds?
I don't.
Okay, so that.
We need higher signal noise data. So I completely agree. We have no constraint. I mean, it's fit nice by Gaussian profile. That's all I can say.
Yeah, I understand that, so that was where I was headed.
Yeah. So we don't know the detailed velocity structure. We need to look if there's multiple velocity components. Right? I completely agree. If these are driving huge molecular winds, that would also be extremely interesting.
Yeah, agreed, they're interesting no matter what.
But people, yeah.
Nick?
I understand your philosophy of trying to use a 1 to 0 line for all of them, but 1 to 0 is, we know that XCO factor, it depends on metallicity, it depends on cone density, it depends on redshift because it's sensitive to CMD temperature, basically depends on anything one can imagine. So I'm just curious, maybe sort of a general question, a philosophical question. Maybe there is a better transition, maybe 3 to 2 or whatever, 4 to 3 are actually better because they might depend less correct as X factors and those transitions might actually be less sensitive to those properties we don't know about.
I mean, in practice, what people do is they correct everything to CO1 to 0, and then they apply
Well,
the
so
X.
it's a philosophical question sort of, because in some sense 1 to 0 is probably the worst of all of them, because it's more sensitive to the CMB temperature, for example.
Well, the isotope lines are better because you can get down to optimal depths below units,
But I don't know that you can detect those.
but they're very hard to detect.
I mean, the clear advantage of CO3 to 2 is that it's brighter. So you can get many more galaxies and go much deeper. This is much fainter.
But
So it's a
still
much harder
okay.
observational slog to go to CO1 to 0.
Yeah,
And there's debate about whether or not it's worth it, right? I mean, it's Justin. I couldn't be here yesterday because actually in Garking talking to the Coney and Rainer Gensel, and they're like, oh, I mean, from their attitude, because they've spent all their PDBI time doing 3 to 2, they don't think CO1 to 0 is as useful because they think that they actually can constrain the excitation reasonably well. I think for kind of normal galaxies, there are very few galaxies of normal star formation properties that have multiple transitions where you can map out the excitation.
well, for sure, the Milky Way when 3 to 2 is better than 1 to 0. The
What?
Milky Way is brighter in 3 to 2 than the 1 to 0.
Yeah, well, the Milky Way is too, but the point is you don't know the conversion, right? So they just assume a factor.
But maybe we should all just use 3 to 2 and forget about 1 to 0. Some kind of historical artifact that people use 1 to 0, but maybe it's actually the worst transition to use.
So you have to recalibrate alpha CO to the CO.
For 3 to 2 and maybe, or 4 to 3, whatever.
Yeah, I know. Okay.
I think
I mean, most of the CO molecules are in the ground state, I think. I think that's true, right? So,
most of them, then why those transitions are bright?
well, they're bright because they're sitting on top of a rising Rayleigh-Jeans tail for the black body, I think, right? It's not just.
I don't think they're all in the ground. No, the carriage, it definitely cannot be because the CMB.
Okay, so we should talk about this. I mean, it was my impression that most of the CO molecules are actually in the ground state. We can talk
Maybe
about
that's
this.
a 0 here.
It's all opaque up to, the 5 to 6
Yeah,
minutes.
these are all optically
6 to
thick,
5
right? So-
transition. But don't you need two transitions, the ratio of 2 transitions to get the temperature, which is kind of necessary to make a correction?
You mean to correct from higher order transitions to lower order transitions? Is that what you mean? Yeah, I mean, and people were doing this. So, for example,
But
in
you
this
don't-
sample, they simply assume a factor of 2 for every galaxy. It's a factor of 2 to go from CO3 to 2 to CO1 to 0. And if you look at this plot here, so this is a factor. So for kind of M82-like excitation, this is a factor of 9 difference in flux. For Milky Way, it's a factor of kind of 2 or 3. They're assuming this correction, right? So their galaxies would be more gas poor if they chose a more highly excited.
So they're guessing at the temperature.
Yeah, basically.
All right, so let's thank the speakers and Greg in the session again.